So welcome again, and thanks for joining us first thing this morning. For those who didn't join us last month for our first session in the series, my name is Jenna Annett, and I work with the Community Energy Association. Again, I just like to give a little bit of background on these webinars, so I just like to quickly introduce CEA and the Kootenay Clean Energy Transition. So CEA is a BC-based nonprofit. We work with local government and Indigenous communities across the province to reduce emissions, conserve energy, and help progress us to a low carbon and healthy future. Next slide there, Rob, please. The Kootenay Clean Energy Transition, or KCET, is a project that was developed to address shifts happening in the energy efficiency, renewable energy, and home comfort space. Through KCET, we want to help Kootenay and boundary communities prepare for a more energy efficient and healthy future through training and capacity building for the building industry, community workshops to help increase knowledge and awareness, and pilot projects that we can test and scale up. So thanks to the generous support of the organizations you see listed at the bottom of this slide, we're offering this free webinar series as part of that training and capacity building piece. Next slide there, please, Rob. All right, so I'd just like to begin our session today by acknowledging the Indigenous peoples from all of the diverse and beautiful places we are joining from. So the land on which I'm currently joining you from is now known as Nelson, but for thousands of years was occupied by Indigenous populations and is the traditional territories of the Sinixt Nation, the Silks Nation, and the Tanaha Nation, and is home to the Métis and many diverse Indigenous persons. I just like to acknowledge with gratitude and respect that the joy I am privileged to experience daily in these mountains and waters is in thanks to their generations of stewardship. And then just next slide there, please, Rob. All right, so with so many of us on the call, I just like to take a minute right away to quickly talk about some housekeeping items. If you have questions as we go through, we do encourage you to just raise your hand and Rob will answer your question right then and there. Alternatively, we will be having a facilitated discussion at the end, so feel free to put your questions in the chat and we can get to them at the end of the presentation. As you would have all noticed when you logged in, we are recording this webinar and we'll be sharing the recording and slides with everyone here via email within the week. It will also be posted on our website at www.shiftshappening.ca, and I'll put that link in the chat so you have it accessible. For those of you collecting CPD points, confirmation email of your attendance will be sent out later today. Okay, so it's with great pleasure that I introduce Rob Pope, a senior consultant with Ecolighten Energy Solutions. So Rob has vast knowledge and experience in the HVAC industry. He's been involved with installing and servicing energy efficient systems since the get-go. So a huge thanks to Rob for joining us today and sharing your wealth and knowledge with us. And with that, I'll pass it over to you.
Thanks, Jenna. You can hear me okay?
We can hear you, yeah.
Okay. Thanks, everybody, for joining in. We're going to be talking about hydronic systems today. So I'll just go through the agenda for the next little while. This is also for new homes and existing homes. We'll talk about gas and electric equipment considerations for new home and retrofit applications. And then we'll do an introduction here to water heat pumps, market context, manufacturers, what to consider for designs, cost, new construction case study, and some key points. And then we'll finish that off with an opportunity to ask questions. And as Jenna said, I'm happy if you interrupt me along the way. I don't mind that one bit. Okay, so let's get started. Forced air or radiant. You know, those are the two general systems. Any kind of heating system can be broken into those two main categories, really. The upside and downsides of each kind of go along the, let's just start with radiant. It's more typical in the lower mainland. It's actually has very niche market in some exclusive areas of North America. There's vast areas of market area that have no radiant heater. Is very uncommon. And then there's others like the lower mainland where the market is concentrated with radiant. there's obviously what architects and house designers like is there's very few drops required for walls. It doesn't impose itself on the aesthetic very much compared to forced air. You can do multiple independent zones. You can zone off a little bathroom on a bedroom ensuite, for example, from a master bedroom. There's no limitation to how many zones you can have, except cost, obviously. When it's installed right, radiant is quiet, you can't hear it. But one of the things about radiant heat, it doesn't do anything for the air, so you have to ventilate the air independently. So you have to have an independent ventilation system. Some of its limitations, it's slow to react. You know, in most cases, it's inflow radiant and you have a topping of lightweight concrete that it's embedded in. And that's still, it's a lot of mass. And it takes a long time for that mass to heat up or cool down. So it has a slow reaction time. If you need cooling in the house, and as houses get more energy efficient, cooling starts to become the dominant load. And so therefore, this is one of the limitations. Radiant can't do, it can do cooling, it can do a partial amount of cooling, but it's complex. But it can never do all the cooling. And so if you need cooling, you need a forced air system to do that properly. Now there are simple radiant systems, but radiant heating tends to be more complex because you're moving water instead of air. You know, so there's pumping, valving, controls, all that kind of stuff. It's a little more complex, and it can be a lot more complex when you add on things to it, like hot tubs, pools, snow melt, that kind of stuff. Radiant doesn't do a thing for your indoor air quality. It doesn't manage indoor air quality at all. Indoor air quality has to do with the air you breathe. And to manage the quality of that air, you need some sort of forced air system. On the forced air side, most of North America is forced air systems. There's quite a variety of indoor air quality options. You can filter that air to the same degree as a surgical operating room if you want. You can purify it. You can manage the smoke from wildfires. You can manage pollen and any particular solid. You can manage air quality very well with forced air systems compared to radiant. And it reacts quickly, you know, where it might take a few hours for the radiant system to heat the home. If you've been away for a couple of weeks and you had to set it back a lot, you know, by the time you walk in the door, turn up the thermostat, it could take hours and hours for all that mass to heat up to the point where you feel comfortable. Whereas with a forced air system, you know, if you're heating air, which is directly impacting your experience of the comfort of the heat, and that's 20 minutes, half an hour, you know, in most cases. It reacts quickly. It's less mechanically complex. You're moving air, so it's not as tricky as moving water. Also, if you've got a forced air system, you can easily add cooling onto that, whether it's an air conditioner or a heat pump. Now you've got cooling in the same ductwork. And ventilation, unlike radiant, because radiant doesn't have any air component to it, you have to have an independent HRV, for example, with all its piping and ducting. Whereas with forced air system, you can integrate it. So you've already got a ducting system there to do the job of providing heat and possibly cooling. Either way, it's a delivery system that already exists. So your fresh air from your HRV, from your ventilation system, can just be tapped into that ducting system. Its limitations, it's not as easy to zone as radiant. And so don't get me wrong, you can still zone. You can still zone very well with forced air, but you can't do multiple little zones. It's just not as easy as it is with radiant. Another limitation is, and this is the biggest one for architects, house designers, builders, homeowners, is drops and furred walls, and what it takes to get a ducting system in a house. That's a challenge. It's a challenge, by the way, that can be overcome with coordination. We'll talk about that later. Also, it has a higher potential for noise. That's not to say a forced air system is inherently noisy. If it's designed adequately and installed properly, it should be pretty quiet. But it's just, you know, we don't have the standards of practice that we do for other kinds of things that go into a building. And so you get such a variety of forced air systems that it's inevitable that you're going to encounter forced air systems that are noisy, not because they're inherently noisy, just because they're not designed well or installed properly. When you get into high performance homes, and when I say high performance, I'm considering step 4 or better. Because right now we're going into step 3 mandatory throughout the province. A lot of jurisdictions have already been to step 3. And step 3 has now become the new kind of baseline. So I'd say step 4 or better. And that's not an absolute threshold, you know, it's a bit of a gray area there. But if you're at step 4 or step 5 or net 0 or passive or any of those, this is what I'm talking about. The limitations and options change a bit. On the radiant side, it's not typical to put radiant in a high performance home. It still has the same benefits that it would have in a non-high performance home, you know, like fewer challenges with drops, you can do multiple zones and all that kind of stuff. But the difference is that in a house built to keep the heat in, it does that very well. It doesn't let it out that easy. Cooling it starts to become the dominant load. When the heat load of a high performance house, because of insulation, good windows, air tightness and all that stuff, the heating load will go down. The cooling load will hardly change at all. It'll be whatever it was, whether you're at step 3, step 4, step 5, more or less. It'll change, but not by much. You still have the same amount of people in the house cooking and cleaning and lights and all that kind of stuff. Your internal loads hardly change at all. And any kind of solar gain you get adds to the heat coming into the building. Now, if you happen to have a radiant system in there, that radiant system, especially in the shoulder seasons, you know, can feel the heat or sense the heat coming in from your solar gain and from your internal gains. It'll shut off the thermostats, of course, but all that mass will take a long time to drop in temperature, and that's the problem. Then you get overheated because the house is so thermally high performing. The equipment options for radiant are essentially the same as it always has been, with one exception, sort of. So we've always been able to put condensing gas or propane boilers in. We still can to some degree with hybrid heating systems. Electric boilers have always been available. Usually in areas and regions where we don't have access to gas, electric boilers have been pretty common. On-demand hot water heaters used in combo systems usually. It becomes your hot water heater for your domestic hot water and for your space heating. This is pretty common. And finally, we have air-to-water systems. That is the exception. Now, that's been around for a while, but not nearly as long as the rest of them. And even though it has been around, it hasn't been a huge demand until recently, until we started getting government imposed efficiency standards. Because of the requirements to hit step code, when we put radiant systems in a lot of cases, we have no choice. We need to put an air to water system to meet the metrics of those step codes. And so that's why recently it's, you know, they popped up on the market a lot more than they used to be. And it's still newish though, you know, we'll talk about that a little later. Just to clarify what I'm talking about mostly when it comes to radiant systems, because there's a lot of variations of radiant systems. But what I'm talking about mostly is the more typical radiant systems. And that is, you can see on the left here, that's, you know, your loops in the floor. And you can see this is on the subfloor before the lightweight concrete's poured over it. Usually it's about 1.5 inches, maybe 2 inches of that concrete that goes over top of this. These loops are all connected to manifolds, and those manifolds have, in this case here in this picture, you can see they have actuators on them. What that means is they're basically valves. If you think about it as valves, they open up these individual loops as you desire, and you can zone off every single loop if you want, although, you know, wouldn't be recommended, but this is where the zoning occurs usually. There's other ways to do it, but this is typical. And the manifolds have mains to go to your mechanical room. Your mechanical room has the usual stuff. It has a boiler, in this case here in this picture, you see a boiler there. And then it has all the piping that comes off of that boiler, the valves, the controls, everything else, the pumps. So that's what I'm talking about when I'm talking about a radiant system. I'm going to focus on air to water heat pumps because that's the technology that's now emerging as the default type of equipment that's going to go into radiant houses. Boilers, as I said, will still be around, but to a lesser and lesser and lesser degree. So here's an image of what you can do with a radiant system. So you got your outdoor unit there. Your outdoor unit connects to your indoor unit. Now that outdoor unit can be do all the work outside, so you don't have refrigerant lines going in. You have plumbing lines. You have heated water going or cooled water, depending on the season. Those are called monoblock systems. Then there's also split systems. It depends on the manufacturer, your choice of which brand to get. The split system, the work of transferring heat to the water happens inside, as is the case in this picture here. The refrigerant lines connect them from outside to inside. That indoor unit, along with a tank, in all cases, with air to water systems, you need a buffer tank. Now this buffer tank has coils in it that can be used to preheat the domestic hot water. Also heating the radiant. It does radiators, it does any kind of radiant. It also does your air because it can provide either chilled water to air handlers, ducted or not ducted, or refrigerant to, depending again on the brand chosen, it can run refrigerant to those units and provide cooling. Can also connect that system into a solar thermal array or a solar PV, but the solar PV would rarely be dedicated just to your heating system. It's, you know, that would be dedicated to your whole house. So here's some issues. The air to water heat pumps currently don't have the same market structure enjoyed by their air-to-air counterparts. And so what that means is there's a lot of air-to-air systems. There's been heat pumps around, air heat pumps around for many, many decades. And so they're common. There's a lot of product out there competing with each other. There's a lot of supply chain. There's a lot of installers that have been doing it and contractors have been doing it for a while. And familiarity with architects, home designers, builders, and so on. So they've been around for a long time, and they're very familiar. Air to water systems, probably we did a study a few years ago for the city of Vancouver, and in that time there was probably, I can count on my fingers how many products were on the market. And of those products on the market, there was only a small handful of them that were actually active in the market. In other words, they had a supply chain, they had technical support, they had products installed and that kind of stuff. Consequently, unlike the air to water heat pumps don't have the scale of contractors that know what they're doing, that are qualified to install these. Relative to the amount of product on the market, we have a very, very short supply. It's a challenge of heating contractors that know how to put these systems in. And there's initiatives going on right now to scale up the market for air to water heat pumps. There are training courses recently, really fresh, that's just been created. People, in some cases, like for example, the city of Vancouver, you have to take that course. You have to get certified just to get a permit to install one. But there is and there's going to be for a while a lack of awareness about air to water heat pumps throughout the industry. And that's across the board. That's with your design professionals, your building professionals, architects, engineers, and so forth, your trades, builders, and homeowners, and authorities with jurisdiction. When you consider the heat pump from a purely fiscal point of view, if you have to put it in, you have to put it in to meet your compliance requirements, that's it. But from a cost benefit point of view, the air to water heat pump is much more expensive and complex than a simple boiler. Part of the reason is the complexity of the technology. The other part of the reason is the product on the market hasn't saturated the market the same way as boilers. Boilers have been around, there's lots of them, lots of competition. Correspondingly, the prices for boilers relative to air to water heat pumps are less. That's probably, as air to water heat pumps evolve in the market and we all get used to it, like we've done with other technologies, that'll change. So here are some of the known brands, and there's a few others. There's a few that escape me always because they're coming and going and coming and going. So at any given time, I could be missing one or showing you one that's no longer around. But as of recently, this is, kind of the idea that I was talking about. What we're looking at here is 1, 2, 3, 4, 5, 6, 7, 8 of them. 8 products on the market right now. So that if I were to show you how many products are on the market for air-to-air systems, I'd need 5 or 6 slides worth to do that. So that's a difference. Key technology considerations when considering heat pump options include. So all air-to-water heat pumps are not the same. Some of them can give you heating and cooling. Some of them can only give you heating, space heating. Some of them can only give you domestic hot water heating, like the sand. Right? Some give you have the ability to heat your domestic hot water completely. Others only have the ability to preheat it. So you see what I mean? There, the choice of the heat pump depends on the, what project you're considering it for. You have to kind of customize your choices. Not all brands are available for all projects. There's quite another thing to consider too is that some heat pumps will only have one or two, some brands will only have one or two products available. And, so you got size 1, size 2, and hopefully one of those sizes works, right? Where others will have quite a range of sizes available. Whatever your choice for radiant heating is, there's a pretty important process that needs to be followed. And I like to think of it as a minimum standard of practice. It doesn't exist everywhere. It's not a standard of practice that is enforced by any authorities with jurisdiction. It is, however, a standard of practice that exists. And there are, luckily, a number of contractors that follow this. But sooner or later, we're going to have to contend with the regulatory requirements for standards of practices to be followed. That might not be this year or next year, but it's coming. And that includes doing proper load calculations. If you don't do proper load calculations, when I say load calculations, I mean the accepted code required methodology for load calculations. If you're not doing that, you're just guessing, and then it's a coincidence if it works. Rule of thumb is not adequate. You need those load calculations to choose the brand and the model within that brand that's most appropriate for the project, that has the right effective capacity, not the nominal capacity. So here's a little thing that I see all the time. Somebody's told, I need a 48,000, my heat loss is 48,000 BTUs. That's 4 tons, 12,000 BTUs per ton. And so you say, okay, well, I've got a 4-ton heat pump, perfect. That's not how it works. That heat pump's nominal capacity is measured at a certain temperature. They're all at that same, measured at that same temperature, which is 47 degrees Fahrenheit. And that the capacity and efficiency of those heat pumps changes as soon as that temperature changes. So as you go down in temperature to your winter design conditions, in a lot of cases, so does the capacity and efficiency of that heat pump. So careful. You have to do your load calculations and measure the effective, not the nominal capacity of the equipment. The other thing is to understand the client expectations. You wouldn't believe how many times we start off with a client talking about their hydronic system that they want. They want radiant floor. That turns out by the time we're finished talking, they didn't really want it. It ends up being a forced air system, right? Now, that's not always the case, but the key is to actually listen, understand why the expectations are there, not just for radiant, for air indoor quality, cost, everything else, right? Budgets, all those things matter, aesthetics. It's really critical to understand the client's expectations so you can customize your system to meet them. Electrical, especially in retrofits, is a big issue, whether or not you have enough capacity on the panel to take on a heat pump. If you had a gas boiler, for example, that would have been a 15 amp circuit, right? If you change that to a heat pump, now you're at minimum 30, 40, maybe 60. It's a big, big difference, especially if you have electric backup heat. The point is this, that the electrical capacity of the house, both in new construction, but especially in retrofits, may be a limitation that has to be figured out. With any kind of heat pump, and air to water heat pumps are no different. Outdoor placements is an issue. In a lot of jurisdictions, there's restrictions about side yard placement, noise bylaws, and so forth. So where you put your outdoor unit has to be figured out. It's not simple. You can't just put it anywhere you like. Hydronic piping, you have to design that. Somebody has to know what they're doing. They have to measure flows and resistance and pump requirements and all that kind of stuff. Auxiliary heat. This is about the electrical panel for one, right? How much electrical heat you need for backup if you're not using a dual fuel system. You could have a heat pump sized to meet the demand for most of the year, except maybe 2-3 weeks, the coldest days of the winter. And then you could have your backup heat take over, which could be a gas boiler. But in a lot of cases, that's going to be an electric strip backup. And that's when your auxiliary heat is an issue, because that electric backup takes a lot of amps, and you have to make sure that you're not overloading the panel. And of course, ultimately, one of the weakest links in our industry for HVAC systems, period, in Part 9 buildings and homes and residences is the commissioning. So any piece of equipment, you know, starts off in a factory, who knows where, anywhere in the world. It doesn't know where it's going to live. It shows up in a box with factory default settings and potentially issues. You know, there might be component failures. Something might have happened on the way there, or something might have happened during installation. Either way, it doesn't matter what. Just before you're ready to hand over that house and that system to the homeowner, it is critical to put the system through all its phases. Make sure especially anything to do with warranty, but generally speaking, you want to do the shakedown. You want to make sure that the system is operating, meeting the design targets that you set out, and that there's no issues that are going to be left to be discovered by the homeowner. That's the last thing you want. And of course, you need to document all that. One, for the manufacturer, if there's any warranty issues, you'll need the documentation from the commissioning. And secondly, you want to establish your baseline. We install the system, here's where all the numbers are, pressures and all that kind of stuff, so that down the road, future technicians can see where the baseline is and where we're at now. Now, I've already alluded to some of this stuff, so I won't spend too much time on it, unless you want to stop me and ask questions, of course. F280-12, actually, that's a Canadian Standards Association standard. So it's CSA F280-12. That is the only accepted methodology. There's a handful of different programs you can use that utilize that methodology, but it has to meet that standard. And that is actually in the National Building Code and our BC Building Code as well. So anything other than that is, it's just a guess, right? How much heat you need and how much cooling you need, room by room. You can see here the graph that shows the effective capacity starting at 47 degrees Fahrenheit. And forgive me for not mentioning Celsius. I'm an old guy, so I claim the right to do both, and I prefer Fahrenheit. The outdoor ambient temperature goes down, and so does the capacity. If you take the performance curves of every one of those heat pumps, they'll all be a little different. Some will be a lot better than others. But nevertheless, you don't know how that unit's going to perform until you dig in and check the performance curves of the unit. And that's critical. You need to know that, because you need to know that to size the equipment in the first place. What size of equipment am I going to put in the house? And after you size that equipment, you need to know that to know what kind of backup heat or auxiliary heat I need, and when do I need that to come on? How much of it do I need? I talked about client expectations already, so I won't go through that too much, but suffice it to say, in my world, if you're putting a heating system in for somebody, it's really important to find out what their expectations are, so you know what to meet, for one. But the other thing that comes up often is expectations that came to the homeowner, for example, from their buddy down the street or Google. You know, it's not always accurate. And so you want to find out what of those expectations need to be corrected and better understood. You know, it'll save a lot of problems down the road. Electrical load, we already talked about that. It's especially a challenge in renos in the lower mainland here. We still have a lot of houses that only have a 60 amp service. You're going to have to upgrade if you're going to put a heat pump in there. And then the question is, well, what's that going to cost? How much to upgrade? And that depends. There's no one number for that. It depends where you are, where the nearest transformer, all that kind of stuff. It's become quite a quagmire in the city of Vancouver and other places because you have no choice. You got to put a heat pump in, right? In a new construction anyways. And so, okay, fine, we got to put a heat pump in. But then there's all these restrictions. Where can you put them? Oh, you can't put it here. No, you can't put it there. No, you can't put it there, right? It makes it tough to meet their compliance requirements. And it really boils down to one thing generally, and that's the sound levels. In many jurisdictions, not all of them, there's a requirement that at the point of reception, which is typically the property line, your neighbor's fence, for example, that the noise of the heat pump cannot exceed 45 decibels, right? And that's what they're worried about. There's ways around that. We have successfully dealt with authorities with jurisdiction to convince them to let us put that heat pump there, you know, because we've measured this decibel level from the manufacturer's data, and we can see that, you know, in that 3 feet or 1 meter or 2 meters from the unit, our decibel level will be at an acceptable level, but we have to prove that. Now, there's other things you can do too. You know, if nobody wants noisy equipment, so A, choose good equipment, quiet equipment. 2, whatever the sounding equipment is, you know, there's mitigation things you can do. You can put hedges. If there is a property line too close to the unit, you can put a fence there of some sort that either absorbs or diminishes the sound so that your neighbor doesn't hear it so well. Don't put it under your bedroom window unless it's an extremely quiet unit. So there's a few strategies like that you can employ. As I said in the beginning, I probably went through it pretty quickly. Generally speaking, there's 2 kinds of air-to-water heat pumps. One is called monoblock. Basically, the refrigerant system in all heat pumps, in this case, in the monoblock case, that refrigerant system is doing its transfer to the waters. It's transferring the heat to the water, all in that one outdoor unit. And so by the time it's done, all you got to do is take that water and transfer it into the building, right? Other units are split, and they'll have an indoor unit and an outdoor unit that are married to each other by refrigerant lines. The refrigerant circuit in those cases is extended into the house, and then it does the transfer to the water inside the house. Now they have their ups and downsides, either of them. Refrigerant, you've got a lot more flexibility where you can put that unit outside because you're moving refrigerant instead of water. With monoblocks, of course, you can't go too far, and you got to be careful about how you protect that water from freezing. You know, you got to put, you know, some sort of antifreeze in your glycol. And you've got the farther distance you have, because it's not under the same pressures as refrigerant, you got to pump harder. You know, there's some restrictions on both. One of the things that is pretty clear, though, is that a lot of plumbing contractors really prefer the monoblocks because they don't need to have the refrigerant tech come in and do work on the heat pump because it's all plumbing. So that's a benefit. The amount of auxiliary heat you need is really critical to understand. In a lot of cases, most cases in BC, you need some auxiliary heat. You're going to have some. Whether it's a boiler, gas boiler, for example, or electric strip doing the backup will depend on a lot of things. It'll depend on how you met your metrics for step code compliance, for example. Right now, you can still do it. You know, if you put a little extra effort into the insulation windows, your building assemblies, and air tightness, you know, those metrics can make it easier for you to put in a boiler. But in a lot of cases, if you're trying to get to step 4, especially step 5, it'll be very, very, very difficult to have a fossil fuel doing any heat in that building unless you really, really enhance your building assemblies, your insulation, your walls, your windows, your air tightness, and that kind of stuff. But it's possible to put in a fossil fuel as your backup. Where it is not possible, an electric strip is your backup heat. Then what you want to do strategically is size your heat pump to maximize its work in the winter. And the first tool you have to do that is use a cold climate heat pump. Those cold climate heat pumps have a special vapor injection circuit in the refrigerant that allows it to maintain its capacity and, to a large degree, its efficiency in sub-zero temperatures. They work really well. We've designed those systems all over the province. You know, most of Whistler these days, that's what they're doing, cold climate heat pumps. And they work surprisingly well. What they do more than anything else, though, is they reduce your requirement for backup. And if you're in the lower mainland or Vancouver Island, they eliminate it completely. Then it becomes optional. So that is something to keep in mind, cold climate heat pump. So here's a pictorial of what is going on with the air to water system. So you can see here on the left, it's just doing your radiant and your domestic. You know, you got your outdoor unit connected to your buffer tank. That buffer tank will have a preheat coil in it. So in other words, your outdoor, your street water comes, it doesn't go straight to your hot water tank. On its way, it goes through your buffer tank, which is a tank full of warm water. So it preheats that city water before it goes to your domestic tank, and your domestic tank has less work to do to get it to temperature. At the same time, that buffer tank is keeping a storage of heated water to deliver to your radiant. Those goldish looking things, those are your manifolds, and then from there we go to your loops. On the right, you have the exact same setup, but we're kind of adding to it cooling. So it's the same outdoor unit, goes to the same buffer tank, same preheat coil, goes to the same domestic hot water tank, goes to the radiant manifolds. But in addition to that, because in this case, and many of them do, they can reverse their refrigerant circuit. So they can absorb heat from outside and deliver heat to your indoor environment during the winter, but they can reverse that cycle and absorb the heat from inside and dump it outside. That's cooling. Basically, that's what an air conditioner does as well. And so what, in this case, what it'll do is it'll reverse that refrigerant circuit when there's a cooling demand, send chilled water instead of hot water to a chilled water buffer tank, and then deliver that chilled water to your fan coils.
Rob, sorry, I'm just going to jump in quickly and give you a little time check. It's 8:45 right now.
Okay,
So just to leave a few minutes for questions, just to keep.
sure. Okay. I think I probably went ahead with some of the stuff already, so I'm not going to stay here. We'll just get through. Yeah, we've talked about this startup and commissioning. I mentioned this before as probably the weakest link. Unfortunately, what happens far too often, not always, but more than it should, is the contractor, spend a lot of time installing the system, and finally it's ready to go. The furniture's coming the next day, and the homeowners are moving in at the end of the week, and you just got a few little things to finish up. You start the system up, you stick, you see it's everything's working okay, and you get out of there, right? That's not good enough. You have to actually go through the system step by step by step by step. You have to at least do the manufacturer's required startup procedures. And there's a bunch of other things that should be done, which falls under the category of acceptable standards of practice. That commissioning just checks all kinds of stuff, right? You need just a checklist. What was the pressure here? What was the flow there? What was the temperature here? No, that kind of stuff, right? That should be documented and left with the equipment somewhere in a way that it's easily accessible down the road. This is not new stuff. There's a lot of stuff, a lot of forms that either come with the equipment or that is easily accessible by any contractor to do a proper commissioning report, or you can just make your own. But there's a lot you can just get offline. An air to water system, as I said before, so I won't spend too much time on it. It has a higher installation cost. Here's an example, if you had a natural gas boiler installed to an existing home, it'll range $6,000 to $10,000. If you want to go from that to an air to water heat pump, that starts at 10 and goes up from there. It's a lot more expensive. When it comes to operating costs, we'll go through this quickly. This is a typical home for 1,000 square feet. What you're going to see here is what it takes to heat it for 1 hour. If you have electric baseboard, that's the baseline. That's a COP of 1, which means 1 kilowatt of heat in, or electricity in, you get 1 kilowatt of heat out. It's 1 to 1. It's the baseline, 100% efficient. It would cost $1.63 in this house. If you get a heat pump who has an efficiency of 1.5, and that's the lower end, your operating cost for that 1 hour is $1.08, and so on. When we get to a heat pump with a COP of 3.5, those are your high-end heat pumps. They're not extremely exclusive. They exist on the market, but they're the higher end ones, the cold climate ones, for example. But look at the cost there. It's 46 cents for that same hour. And if you took a 92% efficient gas boiler, it would be 37 cents. These slides, I think, Jenna, they're going to be available to everybody later, right? Yeah, okay, great. This is a local case study. This was a living building challenge, which means that we were going to try to make this house net positive. I think this was the first one in Canada. We had the privilege of working on this one, built in Vancouver, 5,000 square feet. The load calculations were done first. Of course, this is kind of what it should look like, a typical page of a load calculation. The loads were really low for the size of the house. We put in a Nordic air to water heat pump. That was a split system, has an outdoor and indoor component to it. We put an air handling unit in it to put in chilled water for cooling, and an HRV. And we use Techmark controls to control it. This is what the schematics look like for it. In any project, especially new home, you should see something that looks like this. Somebody somewhere should have done this. And if I was a builder, general contractor, or a homeowner directing the construction, I would want to see that, and I'd ask for that to make sure it was done. You don't have to know what you're looking at. You just want to make sure somebody did it right. Radiant floor design should include, where the loops are going, but also pressure drops, pump requirements, all the technical stuff that the installer needs to know should be there. One of the, we'll go to, where are we here? Okay, so what I want to do is key points. Air to water heat pumps are only appropriate for homes with radiant systems, but radiant systems are not always optimal. When you're talking about high performance homes, you got to be really careful, and you got to do the upside downside analysis. Air to water heat pumps can help projects achieve the greenhouse limits for large homes. This is, it is a lot easier than geothermal to do because it costs less in most cases. The challenges for air to water heat pumps include scaling the market. We talked about that. That's an ongoing thing. It'll happen because it's already in motion, so we know it's going to happen. It will take a while. And then that includes trade training, relationships with suppliers, generating awareness to the industry. That's everybody, builders, homeowners, architects, home designers, and so on. And building a value proposition for air water heat pumps in the face of upfront operating costs. So if you're putting air to water heat pumps in, one of the things is you've got to optimize it. You can't just throw in any size. You got to choose carefully. You got to consider your auxiliary carefully, and so on. So you got to optimize it, not just for performance. That's the first thing, but for optimizing the value that it creates in the home. And I think that's it. Oh, April 25th.
Yeah, great. So our third session is calculating balance points. So that will be on Tuesday, April 25th. I'm just putting the direct link to register in the chat there. So same time, 8 a.m. to 9 p.m. With Rob. Perfect. Thanks very much, Rob. That was a lot of information to get through. So I really appreciate you taking us through that. We did have a couple questions come up in the chat. Colin had asked whether or not they're cold climate air to water heat pumps, but then we did get to that through the presentation. So Colin, I hope that satisfied your question there. And then Richard had a couple comments here. He said that, Rob, you mentioned the noise of heat pumps numerous times. Are air to water heat pumps noisier than air to air? In his experience, air to air heat pumps can be extremely quiet, so much so that none of his neighbors even know he has one. So it's great for you, Richard.
They're no different than air to air. There's some that are good, some that are bad, some that are extremely quiet, some that are extremely noisy. There's really no difference as a category of heat pump between air to water and air to air.
Okay, great. Thank you. And then Richard had another comment here. He just said that his experience in most cases with clients who want radiant heat is that we end up installing two systems because they also want cooling. This doubles the cost of the air conditioning system in a home. In only 2 cases, they've installed just radiant. However, this was done in 2 very well insulated airtight homes with very high-end windows. These 2 homes do not require cooling of any kind at any time. So the cost of doing the super insulated home versus installing a whole home secondary cooling system, in his experience, is not much more. I'm not sure if you have it.
Well, I mean, I'm good on you for finding the magic solution for making a high performance home operate well without cooling and with radiance. I haven't been able to do that. So whatever mysterious magic you're using, I'd like to know about that, because in my experience, it's almost impossible to do it adequately. There's a compromise. If you're doing a high performance home with radiant, it's just hard to do. And to have no cooling load, that's possible. You've got nothing but shady, you get no exposure to solar gain, maybe potentially, and there's just 1 or 2 of you living there, and you really conservative with the use of electronics, computers, lights, and all that kind of stuff.
You make a good comment or a good point in regards to occupants. Yeah, in both cases, it's generally two occupants. So the demand from that direction would be much lower than a family of four or more, for sure. We are in a zone 7 where we do experience 35C days, and it still works. But again, my experience is that it's the temperature differential from inside to outside that makes the difference. We're of course not trying to achieve 20C when it's 35C outside. We're generally in the neighborhood of, in that regard, somewhere in the neighborhood of 28C inside, but still you're appreciating the cooling due to the differential from indoors to outdoors.
Yeah, that appreciation exists when you know what the differential is. Like you step outside and come in and go, wow, geez, there's a lot worse out there than it is in here. But 28C inside the house for the overwhelming majority of people is too hot. And that is in the context, they just spend a pile of money on that house. And relatively speaking, cooling is chump change in most budgets to get cooling in, right? And cooling and heating, combined together as a system is easy to do with a forced air system. And now you've got both.
Right. Yes. Yes. What we found in both of those homes, one of them was done in 2006 and the other one was done in 2017. What we found in both of those homes is that we were looking at, to put an HVAC system in, which neither one of them have other than, of course, HRVs. But to put an HVAC system in was another $15,000 in the cost of the home. Right. So we just insulated them well.
Yeah. Well, in the end, you have to give the clients what they want, right? Because it's their
house. Yep.
So as long as they're informed what the options are, right? That's
yes.
Our job is to do that. And then our job also is to listen to them, right?
Sure.
That's what they want. That's what it would be. I would, in most cases, I would put a little extra effort into talking them out of radiance. Now that
and that's often happens now. Yes.
Yeah, I'm not always successful at that because there's other reasons. Sometimes logic and reason and cost benefit, it's not part of it, right?
Yes.
And so you can't insult the client.
Yeah, what we'll do to compensate, because we do talk them out of radiant most of the time, is we will put the electric heat, Dietrich heat under tile areas, and that really sort of solves most of the issue for people.
That's a good way to go for sure. Yeah.
Yeah, great. Thank you, Richard. We have one more quick question in the chat here with this last minute. And while Rob's answering this question, I'm just going to start a poll. We really appreciate everyone's feedback, and we use it to just to kind of get ideas for topics that you want to hear in these webinar series. But Harvey asks, thoughts on wood boilers? They were popular in the past and don't see them as much at present.
Yeah. Well, I spent an awful lot of years, brought up my family in a rural setting on an island, actually. And so I saw a lot of, alternative styles of heating, and wood boilers was one of them. They seemed to be a viable way to do it in our community because wood was everywhere. Actually, you got to clean up all the alder that's falling down anyways, right? And the easiest thing to do is burn it. But yeah, you're right. I think part of the thing is that as natural gas and heat pumps, natural gas has expanded over the years. Like when I was bringing up my family, there wasn't as much of it in regions as there are now. And simultaneously, heat pumps have become an optional technology in those areas. So for example, where I brought up my family on that island, now it's a no-brainer. It's a heat pump that goes in. Even if you have a lot of wood on the property, like I did, and there comes a time where you get sick of it, schlepping that wood in and bucking it up, and or you buy it, cord of wood, and it's ridiculous how much it costs, right? In all cases, the heat pump is more cost effective. Plus, it's still running whether you're there feeding it or not, right? So other than that, I'm not sure why those wood boilers have almost disappeared. It might be just my consciousness of them, but they don't seem to be around as much.
Wonderful. Thanks, Rob. And we'll just call it there. It's 9:01. So thanks everyone so much for joining us today. And hope to see you again at the end of next month for our third and final session on calculating balance points. And again, thanks, Rob, so much for imparting all your knowledge on us.